Hello guys, in this video we will understand how transaction works in DynamoDB. First we will understand why transactions are needed, then problems with transactions and scalability in NoSQL systems, design goals for DynamoDB, the architecture and the final result. This video is actually a summary of the actual talk given by Doc Terry. I'll give the link in the comment section. Now let's understand why transactions. I think it's very easy to get it because in our systems there are always some invariants or conditions that has to exist between multiple items in a system. For example, if a person A gives money to a person B, right, then this entire transaction where money getting deducted from a person A account and getting added to a person B account should happen atomically, right? And these type of things exist in our systems a lot, right? Like this money transfer example, correct? So we need transactions in our system, and that is why DynamoDB team also thought of adding transactions into their system, so that much more people from SQL background can move to these systems that can scale with predictable performance without letting away their transaction part. Right? Now, problem with transactions in NoSQL, specifically Dynamo. So, Dynamo has a core goal of providing predictable performance and unbounded growth. So, if you see here in this graph, right, by default, the get input API gives us predictable performance with unbounded growth. For example, even if you have 100 MB of data or you have 1 TB or 100 TB of data, your get input API latency will not increase, right? So when they wanted, the Dynamo team wanted to add transaction into their systems, they don't want to get into a state where the predictable performance is not there when the number of transactions are huge, right? And also they don't want to get into common problems of transactions like deadlock, starvation, right? So they don't want to get into this. Currently, other NoSQL systems provide some restricted way of doing transactions. For example, restricted to a single partition rather than because how NoSQL scales is dividing your data into different partitions, and one partition resides on one machine, physical. So it's easy to do a transaction into a single partition, as we are doing this for many years with Postgres, MySQL, and other systems, right? Some provide restricted isolation guarantees, right? Rather than providing true isolation between transactions. Or some say we will provide only on known partitions table, right? Which is not what is required for Dynamo. Uh, Based on those limitations and the core goal of providing predictable performance with unbounded growth, these are the goals DynamoDB team set for themselves. Execute set of operations atomically. Atomically is needed because we are doing it in transaction way, so atomicity has to be there. Serializably, where the isolation parts comes, that two transactions working at parallel with each other, right, working on the same data sets, should exhibit a serializable nature, isolation in a way where they could be depicted that the one transactions happened before other. For any items in any table, when we say any items in any table, that means the transaction should be applicable not on a single partition but across partitions across any tables into the system. I have not mentioned, but this is within a region that we are talking, not across regions right now. And again, the most important is with predictable performance and no impact on known transactional workloads, right? So these are the core goals that the Dynamo team set for themselves. Now let's look at the standard approach of implementing transactions, right? The most that we have seen. First is how we write transactions is by starting transaction into the system, then write our set of steps, in which you'll read some entries from the DB, do some manipulation, and then update those entries back into the DB, right? And some in some cases there is an inherent transaction into the system, right? Where we do not explicitly say this is a transaction, but system inherently implemented as a transaction. We use two-phase locking, which means we lock the rows on which the exact internals of two-phase locking we are not discussing here. You guys can go and read, but fundamentally we are saying it is a lock-based approach where a system takes locks first and then do some operation and then release locks before the commit. And then two-phase commit is what is required when you are doing transactions across different systems, right? Like in different partitions in a NoSQL system. And multi-version concurrency control is a very important part of many SQL and even some new SQL systems where it allows multiple interactions to work in parallel where still the interactions do not see the state affected by other interactions, right? So this allows the interaction to read whatever state was there into the system when they started working on that system. So they can read from the snapshot of their time, right? This approach was actually rejected by the DynamoDB team, right? The primary reason for this approach is for rejection of these approaches is one is with two-phase locking, there is a chance of deadlock, right? And in case of because you are locking a set of operations or locking us so many resources into the system, right? So providing that predictable performance becomes difficult, and same is the case for multi-step transactions where if you can run your transaction for 5 hours or 2 hours or like this is a big enough time, but if let's say you're running your transaction for 2 minutes even, right? In those cases, it becomes very difficult for the system to behave with a predictable performance in a multi-tenant environment, right? So the first thing that DynamoDB team does is they introduced or implemented one-shot transactions, where rather than holding up a transaction open for a long time, you have only two items to deal with. One is a transact get items where you can read a set of transaction, read a set of tables, right? You cannot do any write in this. And then there is a transact write items where you can update, delete, or insert a new entry while checking certain conditions into the system. So the benefit of these one-shot transactions is because you are not asking the system to hold or open a transaction for a longer period of time. You are submitting the entire transaction batch at once, which means in a shot, right? Now the system can predictably apply these things, and the time to apply these things will only depend on number of writes that we are doing or number of reads that we are doing into these items. Uh, so let's see one example of how this one shot transaction would work in case of a money transfer case, right? On the left hand side, it is a traditional system where you'll begin a transaction, you'll read a value from Mary Money, then you'll read from Bob Money, then you'll increment and update Mary Money by 50 and Bob Money by minus 50. Right? The same thing could be done via one-shot transactions. You first read Mary Money and Bob Money, right? You check certain condition, then you write onto the system saying Mary Money is Mary Money minus 50, right? And the current balance should be the one which I have read while reading this data. So there's a check conditions, and again for the Bob money also it is minus 50, but again it checks the balance that it should be the one which I read. Right? So in this way we can represent most of our common use cases in transactions where we generally read data, do some operation and then put by doing these in one shot and rather than blocking the entire system. So in one-shot transactions, unlike interactive transactions, which can block resources for a longer period of time, Dynamo team chooses to use one-shot transactions, which can give us more predictable performance because it is not locking any system for a longer period of time. The second thing that they used is timestamp ordering for serializability. I suggest timestamp ordering itself is a complete topic in itself. So, if you guys want to understand more about timestamp ordering, let me know in the comment section. But in general, timestamp ordering is also one of the techniques which provides isolation when multiple transactions are working in the system, right? Like 2PL, two-phase locking is also one of those techniques. So for isolation, Dynamo team uses timestamp ordering, which helps that there are no deadlocks into the system. Independent serializability, which means when there are multiple parts of a single transaction working on different partitions altogether, but they don't need to interact with any other to get an overall serializability of the system, right? And one more important aspect for Dynamo DB team was because they provide in place upgrades to the newer features or newer things into the system, right? If they would have used locking in the first place rather than timestamp ordering, it would be very, very difficult to update their system in place without any downtime or any problem whatsoever. Right? So because it's a multi-tenant system also, they like wanted this to be completely free from all these problems, and that's why they went for timestamp ordering. For atomicity, like which means if a transaction will commit, then all of the portions of the transaction should commit or none of them, right? For this, again, they are also using something very similar to two-phase commit only, right? So in the first part, let's go back to our example again, right? So there are two persons we are writing to. One is Mary money that we are writing, and one is Bob money that we are writing by checking certain conditions. Let's assume these two are on different partitions, right? So in first part, in first phase of this two-phase commit, uh, a transaction coordinator will send this request of uh, committing this transaction or accepting this transaction actually to every partition, right? Every partition either has to accept or reject those transactions, right? If all the partitions has accepted those transactions, then the next phase starts, and this is where it asks every partition to commit those things, right? And now because these transactions are also working, somewhere a ledger, durable ledger has to be maintained so that these transactions are not lost. Interestingly, DynamoDB team uses a DynamoDB itself as a ledger for the transactions into the system. And because of independent serializability that we have seen in the timestamp part, right? The time taken by a transaction is linear with number of operation in the transaction only. Now let's see the architecture of how transaction were internally implemented, right? So whenever your app gives any request to DynamoDB system, first of all, it gets routed to a request router, right? So there are these n number of stateless request routers which are in works, right? If you send a request to a request router which is not part of a transaction like traditional get and put, right? This request router will directly talk with with the master node of a partition. So I have shown three nodes primarily just to show there is a master and there are two slaves in there, right? So in this case, there is no transaction coordinator coming into place, which essentially means no impact on known transaction items. For transaction items, every request goes to a transaction coordinator, right? Which performs, let's say, two-phase commit between two different partitions. And to maintain consistency of this and durability of this, a ledger is maintained, right? And at any time, if this transaction coordinator goes down, because this ledger is maintained in a durable manner, right? A process keeps on checking if there are any pending transactions and give that input to a new transaction coordinators, which will take the transaction and complete it, right? Interestingly, because we are using timestamp ordering in this case, and these nodes provides a guarantee that even if you ask to apply a certain transaction multiple times, I will apply those transaction exactly once, right? So there are no race cases even when, let's say, multiple transaction coordinators are trying to apply the same transaction. So this way, the Dynamo team achieves atomicity, isolation, and the major factor that they wanted to implement is predictable performance in DynamoDB even with transactions. And at the same time, because the path for normal get and put are separate, right? So no impact on non-transaction aspects, right? With that said, we can see that the outcome which Dynamo team wanted to achieve, that predictable performance even with transaction and or unbounded growth, they are able to achieve this thing here. So even with the number of transactions growing, right, the latency remains constant, and it is only a factor of number of operations that we are doing in that transaction, right? And generally those number of operations are less, like 2, 4, 5, 10. You generally don't want to build a system where you're doing transactions on thousands of entities at a single time. So they are able to achieve transaction and scalability into the DynamoDB system. To understand more details of how this timestamp ordering is working and how this conflict management and isolation is handled within DynamoDB, let me know in the comment section and I'll provide a separate video on the same. Thanks guys, thanks for watching the video.